Okay, so let's start off with a couple really quick examples of just taking capacitors in series and capacitors in parallel, and then we'll combine the two into a single example. So let's say we have two capacitors. We'll say three capacitors. And I'm saying capacitors, I'm writing resistors. Let's say we have three resistors. We'll say the first resistor is a 1 ohm resistor, the second resistor is a 2 ohm resistor, and the third resistor is a 3 ohm resistor. So let's do two things. Let's find the equivalent resistor if they are in series, and let's find the equivalent resistor if they are in parallel. So to begin, let's start off with a sketch of our resistors. Actually, let's start off with our resistors in series. So this will be part A. My recommendation, and I ask you to always sketch your electrical components. So first, sketch your components. Label your components. I'll label this resistor R1, this one R2, this one R3. And we want to know what the equivalent resistance is. Well, remember, for resistors in series, and I'm going to call my equivalent resistor R123. So for resistors in series, the equivalent resistance is just the sum of the resistances of each of the individual resistors. So in this problem, I'm going to just say that we have a 1 ohm resistor and a 2 ohm resistor and a 3 ohm resistor. This is the easiest example we could possibly do. And we add those together, and our equivalent resistor is a 6 ohm resistor. So we could replace those three with a single one rated at 6 ohms. Pretty simple, pretty straightforward. Well, now let's take these three resistors and let's wire them in parallel. So here's my diagram. I'll just call this resistor R1, this one R2, this one R3. And I know that my equivalent resistor for resistors wired in parallel, its reciprocal is equal to the sum of the reciprocals of the individual resistors in parallel. So for this one, I'm going to just do my algebra out. I know my common denominator is going to be R1, R2, R3. So that's the product of the individual denominators. And I know my terms. The first term will be the product of R2, R3. The second term will be the product of R1, R3, and the third term will be the product of R1, R2. So this means that our equivalent resistor has a resistance of, well, in the numerator, we have the product of the three resistors, and in the denominator, it's the sum of the products of the pairs of the three different pairs of resistors we have. Now, what I'm going to do on this one, and I want you to start getting in this habit whenever you're working with circuits. If you see that a component's value can be expressed as a multiple of another component, express your variables in terms of that component. So you have fewer number of variables. Right now I have 3 variables I'm working with, but I see that I could call the first resistor, we could call the first resistor R. The second resistor is 2 ohms, so it has twice the value of the first resistor. The third resistor is 3 ohms, so it has 3 times the value of the first resistor. Now, why I do this is because when we get more and more complicated circuits, it often simplifies the algebra because we have fewer variables to keep track of. And a lot of times, those variables quickly cancel out. We don't really need to do it for this example. It's kind of overkill for this example, but I want to practice it on this example so you can start getting used to representing things as multiples of other things. It will eventually save you time. So with that said, let's turn to this R1, 2, 3. So R1, 2, 3, and I'll just rewrite this. And in fact, quicker than rewriting, well, I'll just continue. So R1, 2, 3 is the product of the 3 resistors plus the sum of the products of the 3 pairs of resistors. And I'm just going to reduce it down to a single variable for practice. R1 we called R. R2 has 2 times the value of R. R3 has 3 times the value of R. This is divided by R2 times R3, so that's 2R times 3R, plus R1 times R3, so that is 1R times 3R, plus R1 times R2, so that is R times 2R. Now, notice what we have here. We have in the numerator 6R cubed. In the denominator, let's see, this is 6R, this is 3R, 6R squared rather. This one is 3R squared, and this one is 2R squared. So in the denominator, what is that? 6 plus 6, that looks like 12. Now, never trust my simple math. I make the silliest of mistakes. I can't tell you how many times I've made things like 2 plus 2 is 5. So always double check my algebra. So I see we have 6R cubed in the numerator, and things look good to me. So don't hesitate to speak up if I made a mistake. So notice what this allows us to do. Look at how clean this is so far. So this allows us to take 2 of the r's in the denominator, the r squared, and cancel with an r squared in the numerator. This leaves us with the equivalent resistor being equal to 1/2 R. In other words, 1/2 of 1 ohm, we could replace those 3 resistors in parallel with a single equivalent resistor. And that's great. We could save our materials. We could save our trips to the store to buy additional resistors if we could somehow, if we have a single one that matches what we need. Or the reverse is true. Let's say you need a particular value of resistance, but that value, you may not be able to get it just from a single resistor. But if you have 2, 3, or more resistors, you could probably think of a way to wire them in parallel, or maybe a combination of wiring them in series and wiring them in parallel to get the value that you need.